Thank you, everyone. So my name's Kate, and I'm an Astro 3D postdoc working with MAGPI, SAMI, and the Genesis teams. Now, following on from Kara's excellent overview, I'm going to be summarizing the aims of the theory stream of the MAGPI survey. And of course, I'm giving this talk on behalf of an ever-growing list of collaborators as listed here. Okay, so in the next 10 minutes, I'm going to convince you that the theory stream of MAGPI is really important. So I'm going to be going through what MAGPI is. I'll explain why we want comparison-ready theory data, how we're making this suite of data products, and what we're hoping to do with them. Now, obviously, that first point has just been covered by Kara, so I don't need to go into the details about the observational side of this survey, but I will take this opportunity to highlight that a really broad theory component has been included within the MAGPI survey from the start. And the comparisons that we're going to do with this project are really novel. We're constructing a full suite of comparable MAGPI data products from a broad range of hydrosims from all across the world. This has totally been enabled by Astro 3D, but I have to take this opportunity to thank the PIs of MAGPI, so Caroline Foster, Claudia Lagos, Emily Wisniewski, Trevor Mendel, and Tian Tian Wan for giving me the chance to be part of such an exciting project. Okay, so moving swiftly on to why we want this theory-ready data comparison data. And I think the first figure from our survey paper that came out earlier this year does a really great job of justifying this. So here I'm showing you the evolutionary history of the spin parameter in 3 separate simulations. We've got the Eagle simulation on the left, Magneticum in the middle, and Horizon AGN on the right. Along the y-axis, we're looking at look-back time, and that red box is highlighting that key period in time for our MAGPI observation, so about 3 gigayears look-back time. And on the x-axis, we're looking at the spin parameter. The color map density plot in the back is giving you the number density of galaxies with that given lambda r. So just as a quick reminder, lambda r, low lambda r have highly dispersive orbits. The rotation support is highly supported by dispersion, so you get very round objects, and things that have high lambda r's at the other end of the x-axis is those things that have highly coherent orbits that settle into a disk. Okay, so our 3 different simulations are predicting 3 different things, and particularly if we break those simulations down break the galaxies in those simulations into high and low density galactic environments, we can see that we're predicting a different environmental dependence from each. And that's really cool. Our cosmological simulations are going to be a really great tool for exploring these different theories of galaxy evolution. And the MAGPI observations are going to give us an epoch at which we haven't had stellar kinematics before. And we can use those observations to test and evaluate each theory. But it's really important that we make sure that this is done in a fair and consistent manner, because it's not a case of this simulation gets it right and this one gets it wrong. There are a huge number of threads to untangle. So these are the 5 simulations that we're currently working on with the MAGPI survey. And all of these simulations broadly get to the same answer by redshift 0. They're broadly reproducing the observable universe. And I'm just going to show you the stellar mass functions at approximately redshift 0 in order to prove to you that they're all approximately getting that knee in the stellar mass function. They're basically getting to the same answer. But again, they're all using slightly different recipes to describe the underlying physics. So here I'm presenting you my simulators cookbook. I have a series of different ingredients necessary, the key ingredients necessary to build your hydrodynamical simulation. You have prescriptions for things like star formation, metal cooling, what happens when stars explode in your feedback regimes, how does your AGN give energy out, and even things like how we model mass in our simulations. Now, full disclosure, this plot is very much inspired by one of my colleagues, Jess Thorne's figure for depicting variety in SED fitting methods, and you should have a look at her paper that's at that archive link. But for simulations, I'm going to go ahead and put in all of our simulations from MAGPI, and you can see very quickly, although our basic ingredients are the same, we have very tangled threads here. Everybody's using a slightly different formalism, And so the variety and complexity of these recipes can make it really difficult to understand, okay, which element is key to reproducing our observations? And to get to the bottom of this, it's really important that we make sure that our comparisons are made fairly, not just between our observations and our simulations, but between just the simulations themselves. Okay, so I've told you we need these, so how are we going to build them? And I've been attempting to do this using the code that I wrote during my PhD called SimSpin. Now, I wrote it over the course of my PhD, so naturally I spent the first year of my postdoc rewriting it into a better package. It's all open source, and you can find it on GitHub. It's fully tested and documented, and there's going to be a large number of longer walkthroughs coming out soon on the archive with the public release of version 2, which you can find on the dev branch if you're interested. But what does it do? Okay, so SimSpin is a virtual telescope, and it will take a galaxy model from your Hydro Sim and produce an integral field spectroscopic observation in the format of any telescope that you want to mimic. So obviously in the case of MAGPI, we're mimicking the Muse VLT. So anyone who's unfamiliar with IFS, hopefully by the end of this session, you should have an idea, but just in case. So IFS, you're laying a series of optical fibers across the surface of your galaxy, and you feed each of those optical fibers into a spectrograph so that we get a spectrum at each pixel in our image. We can then use templates like Sam was showing us to fit each spectrum for the underlying stellar properties, things like ages and metallicities. And we can fit the line of sight velocity and dispersion to each spectrum based on how far it's shifted in wavelength space. Now, SimSpin can mimic this using the known particle properties that I get from my simulation, so things like particle velocity, ages, metallicities, and reverse engineer the process to produce a spectral data cube. Alternatively, we can also meet observers in the middle. So rather than reversing the process all the way to those spectral data cubes, we can produce what I've called a kinematic data cube. And when we're generating these, we do sort of the same kind of process. So we're gridding up our particle simulation and we're gridding it up into spatial locations, just like those optical fibers that we've placed across. In each pixel, we then take those particles that fall within that pixel. We give some observational uncertainty to each velocity and produce along the line of, along our z-axis, instead of wavelength, we're now creating a velocity distribution. And in this way, we can create a data product that's a bit more similar to the maps that you would get after fitting your spectral data cube with observational software like PPXF. So pretty pictures, because SimSpin, the idea is that it's like a telescope. So here we've got an image of a galaxy from Eagle, and here I'm just showing you some of the variety of maps that we can produce. So here we have some mass-weighted gas maps. And on these gas maps, we've got specific star formation rate, metallicities, line of sight velocities, and dispersions. We can produce the same for the stellar component in our galaxies, so mass or luminosity rated. And here we're looking at ages as well, and metallicities. And then, of course, we can produce these spectral data cubes from the stellar component of our galaxies and look at them just like we would with observational software. So here I'm looking at an Eagle cube, but using QFitSphere. And of course, you can then, one of the benefits of this is that you can run these simulated models through your observational pipelines and check that what you get in is what you get out. Okay, so I've told you that I'm going to build a bunch of data products, but what's the plan for them? And this is sort of one of the novel things about MAGPI at the moment is we want to do a theory data product release. So it's sort of novel for theory. It's a little bit less novel for observational surveys, obviously. But the idea here is that we're going to be producing a variety of data products, and we want them to be well documented and clearly in a consistent manner across all of these simulations. So it seems only reasonable to produce that into a paper and release it to the public. We're also hoping to be able to have some kind of like web portal so that you can go and access this data, produce it at a variety of different wavelengths, epochs like time axis, not wavelengths, in order to look at how these structures are evolving across time, because that's the other thing that these simulations give us access to. Cool, so I think I may have rushed, I think, oh, cool. So that's pretty much it from me. In summary, Hopefully I have convinced you that the theory stream of MAGPI is going to be really useful for getting to the bottom of theories of galaxy evolution. Those simulations are giving us a way of testing, and our MAGPI observations are giving us a previously unexplored epoch in time. However, it's really important that we make sure that these comparisons are made consistently, both between observation and simulations, and between just our simulations alone, because there's a lot of different processes that are being incorporated into those simulations. And then finally, these simulations are going to give us that access of time to be able to explore how we get from the MAGPI epoch to epochs like Manga and Sami, connecting everything through time. So that's everything from me. Thanks again for giving me the opportunity to talk to you guys, and I'll take any questions.
Great. Thanks so much for that really excellent talk, Kate. So there are a few questions on Slack, starting with Julia. She asks, having theoretical data releases sounds amazing. Will they be publicly available?
Yes, of course. Yes, this was there's a slot in Data Central for MAGPI and a sub-slot in that group for the theory data products. So they will all be made publicly available and, of course, obviously documented and stuff. So.
Okay,
yep.
Great. Cat Strott asks, can SimSpin do calibration errors, etc.?
So I guess on Slack, Kath, if you could specifically or specify what kind of calibration errors you mean, but in terms of observational uncertainties, you can incorporate things like a velocity, the line spread function of your telescope. You can incorporate observational seeing conditions. Obviously varied spatial gridding. So MAGPI and Muse data has a really high spatial resolution, but Sami has a slightly lower spatial resolution, and you can of course pick your telescope depending on which one you want to, what kind of observation you want to mimic. But yeah, I can answer that better online, I guess.